Welcome everybody, GOBC Chem 114, talking about what lipids are. Um, so let's get started. We introduced them in the last session, and thinking deeper about this is lipids or fatty acids, which make up lipids, one form of a lipid. They all can come together and they can sometimes stack really neat like this organized group of potato chips. And then in other cases, they can be irregularly shaped and they don't fit so neatly and close together. So we can draw these structures of fatty acids. We also know that they can be saturated or unsaturated. And if they're saturated, they have hydrogens that to take up every single space that the carbon can when there are no double bonds. If we have double bonds, we are lacking some of the hydrogens that could possibly be placed, and we have alkenes, which means that we have an unsaturated lipid or an unsaturated long chain fatty acid. So these can be very long. The fatty acids can be up to 12 to 18 carbons long. They're insoluble in water because of their long chain. It's much longer than 6 carbons. If they're saturated, they do not contain any double bonds, but if they're unsaturated, they will contain C double bond C in the carbon chain. So be, learning what you have already, you know what unsaturation is and you know what a double bond is. They go hand in hand. Um, Thinking about the structures of these molecules, we've already know the generalized structure. It has a carboxylic acid and a whole bunch of carbon and hydrogen attached to that carboxylic acid when it is a fatty acid. Okay, so we have here, we have 10, 11, 12 carbons. We could write that same molecule a little bit differently here, such as CH2, 10, CH3, and then this can be COOH. These two happen to be the same molecule written a different way. So you can write the formulas and structures in different ways, just as we've done with other molecules. Here is the ball and stick model at the top, and they call this lauric acid, right? And so you can count the carbons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Guess what? All of these are lauric, all three of these structures are lauric acid. Lauric acid we've used for a couple of experiments, I think. It's a naturally occurring molecule. It has some important uses, as do all these fatty acids. Now we have an even longer chain. Um, it looks like a longer chain, but guess what? It's not. It's the same thing. It's lauric acid again, but in the condensed structural formula, it's completely written out. So it may look like it's different, but it's not. So be careful you don't get tricked. Maybe that could be a question. But be careful you don't get tricked because this one and this one, they have exactly the same number of carbons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then here's the line angle formula of lauric acid. So every single structure here is the same molecule. Think about that. That is how, remember I said chemistry can be redundant? I'm sure, I don't know if physics has the same problem. I wish I was more of a physicist. But no, they are all quite similar, right? So moving on, um, just now that you know different ways to write these molecules, we take a little bit of a look at their properties, their melting point, physical properties and such. And so lauric acid, which we just looked at, has a melting point of 44 degrees Celsius before it starts to become liquid from a solid. It's present in coconut. Myristic acid has 14 carbons. It's a little bit longer than what we just looked at with lauric acid. It's in nutmeg. It has a higher melting point of 55 degrees Celsius, and that makes good sense because it's 2 carbons longer. We look at palmitic acid. It's 16 carbons long. It's found in palm trees and such, and can be used for cooking, or some variant of it. This one has a melting point of 63 degrees Celsius. And then we have stearic acid. it has 18 carbons. It's found in animal fat. So as humans have it, it has the highest melting point because it has the most carbons, and it's 69 degrees Celsius. And what we get is a lot of interactions between the nonpolar parts of each molecule interacting with another molecule of itself or one similar. So these are all saturated fats. They have as many hydrocarbons as can possibly be placed on the carbons. There is no unsaturation here in these fatty acids. Well, what happens if we introduce unsaturation or we put in a double bond? Interesting. They actually become more fluid. They can't stack quite as well. So notice how the melting point is lower. The interactions are minimized because this kink, this double bond introduces a kink in the structure of the fatty acid. So palmitoleic acid based on palmitic acid again, still has only 16 carbons, but it's now at 16 to 1 with respect to double bonds. And then we have oleic acid, and it's 18 to 1, so it's even longer, and it's found in olives, pecans, and grape seeds, and its melting point is lowered quite a bit as well, even compared to the saturated fatty acids. This unsaturated fatty acid is hardly below room temperature. It is below room temperature, so it's probably liquid if you're at 23 degrees Celsius. And of course, palmitoleic acid will be a liquid because its melting point is 0 at room temperature being 23 degrees Celsius. So fatty acids can be unsaturated with only one double bond, but you don't just have to have one double bond, you can have more. And one of the key things, if you start counting from the carboxylic acid to the first double bond, 1, 2, 3, 4, 5, 6, 7, 8, 9, again 1, 2, 3, 4, 5, 6, 7, 8, 9, you'll find that the ninth carbon from the carboxylic acid is where the point of unsaturation often begins. But we will actually label, in many cases, from the other side of the carboxylic acid, contradicting what we've been doing to label where the points of unsaturation are. We'll see that in a second. So it's a little confusing. Um, but more of these with more than just one double bond with more than one point of unsaturation. This one has 2 double bonds. This one has 3 double bonds. This one has 4 double bonds, right? Linoleic acid, linolenic acid, arachidonic acid. Notice these two names are similar only because they both have 18 carbons, but one has only 2 double bonds, the other one has 3, right? So it's more, it has less interaction and less favorable stacking. But the melting points are super low, so they're liquids even at freezing. So -5 degrees Celsius, this is a liquid. -11 degrees Celsius, this is a liquid. And then finally, arachidonic acid, which we're going to find out is active in forming what they call prostaglandins and eicosanocydes, which are like hormones. They are hormones and it all comes from the starting molecule here, arachidonic acid, which has 20 carbons and 4 of them are unsaturated. So, wow, this is very liquid, very useful in freezing temperatures because it will stay liquid all the way up to -50, right? So animals and humans might like the use of arachidonic acid. And so we can see the trend here. And linoleic acid is found in soybean and sunflowers and safflower. And linoleic acid is found in corn and corn oil. And arachidonic acid is found in meat, eggs, and fish. So we just looked at unsaturated fatty acids and more of an explanation for why there's a kink. Remember the cis-trans double bond stuff we talked about previously? I didn't teach that to you for no reason. Look at this. This is a cis double bond. Look how that affects a molecule. It makes it like kind of triangular pyramidal overall. When you look at it, it's like a big hill. And these molecules have a hard time stacking together, although they can on the side. They lose some ability to interact with other molecules like itself. especially at higher temperatures. And aldehydic acid has a trans bond, and the effect of a trans bond is it almost makes it a lot like if it were not unsaturated, but it is still unsaturated. It has a double bond. So cis and trans isomers of a molecule are important. Both of these are the same. These have the same chemical formulas, but their double bond makes them a different molecule. Many of these are naturally occurring. Okay, so again, carbon 9 seems to be the magic carbon where suddenly you get that double bond introduced. That just seems to be the favorability of fatty acids in nature when they have unsaturation, cis and trans. So we humans can synthesize many fatty acids from carbohydrates and other fatty acids, so we can use these sugars and our fatty acids we get in our diet to make more fatty acids. But there are some fatty acids that are polyunsaturated that we cannot make in our body, such as linoleic acid, linolenic acid, and arachidonic acid, some of which we just looked at. These polyunsaturated fatty acids must be obtained from our diet. So we have to go out and make sure we get the things we need to survive well and be healthy. Properties of saturated fatty acids. Well, if they have no double bonds, therefore they're saturated, they can stack and fit close together. Because imagine you have a mole of fatty acids, you have gazillions of these molecules, right? There's strong dispersion forces. Remember dispersion London forces? Well, there's so many carbons that these carbons end up interacting with each other in short monetary uh, interactions of a dispersion force where there's an induced dipole for only a second, not a second, but a femtosecond, 1/15th of or 1 times 10 to the negative 15th of a second. That's almost unmeasurable. These have higher melting points and are usually solids at room temperature, right? Because they have no kink and they can stack well together, like the chip analogy. So again, stearic acid, saturated, all the carbons have all the hydrogens they possibly could, no points of unsaturation, all saturated. They stack nicely together and they tend to have higher melting points. But when you introduce these double bonds and points of unsaturation, the molecules cannot stack as well and they are more liquid and more able to move with respect to each other. So interesting. A cis double bond introduces a kink. Here's a cis double bond in oleic acid, and it raises, it actually lowers the melting point, and so it doesn't stick together as easily, and it melts much easier. Lower melting point for unsaturated fatty acids versus saturated fatty acids, which have higher melting points. So let's take a look at oleic acid again with this maybe trans double bond at carbon 9 from the carbonyl. And why is this molecule an acid? Well, it's because of the carboxylic acid group. How many total carbons are in oleic acid? Well, if you count this up, 1, 8, 9, 10, 17, 18. Now there was a mistake there may be a mistake there where that says 5. That should not be 5. That should be a 7. I had to correct that. Hopefully you guys note that. So there are, every once in a while, there are mistakes in these slides and I try to fix them. Is this a saturated, monosaturated, or polyunsaturated fatty acid? You should say it's unsaturated. It's monounsaturated because it only has one double bond, so it's not polyunsaturated. Is it likely to be a solid or a liquid at room temperature? You should say it's probably a liquid because of that double bond. Would it be soluble in water? Probably not, because it's very nonpolar with a bunch of carbons and hydrogens, and it's way beyond 6 carbons, so it's insoluble in water. And so, yes, a carboxylic acid function makes it an acid. It has 18 carbons if you count this. Again, it says 16 in the mistaken slide. That is not correct. This is the corrected version. So is it a saturated or monounsaturated or polyunsaturated? It's monounsaturated, just one double bond. It doesn't have two, so it cannot fit the polyunsaturated definition. Is it a solid or a liquid at room temperature? It's probably a liquid because of that kink. Remember, this is a excuse me a cis double bond. It doesn't stack quite as well as if this was missing and it was just a saturated single bond. And is it soluble in water? Well, no, it's not. It's just too many carbons. It's insoluble in water because it's way beyond 6 carbons. Okay, looking at these interesting molecules that come from arachidonic acid and make a ton of different molecules through metabolic processes. So now we're getting into the biological chemistry part of this class. Prostaglandins come from arachidonic acids. They are also called eicosanoids, and they are hormone-like substance produced in the cell, and they have a root of using a long chain unsaturated fatty acid, by the way. And this arachidonic acid is polyunsaturated and it's 20 carbons long. Um, and then it has a 5 carbon ring to it, just crazy. When it becomes a prostaglandin from arachidonic acid, it introduces a 5 carbon ring. And enzymes often do this. Enzymes do the chemistry in our body that we would do in the lab using heat and acid or base or whatever. Enzymes do all that, and enzymes can actually hide the acid-base chemistry that we didn't learn about until we examine the enzyme more closely, and it's really using acid-base chemistry as well. That comes with enzyme mechanisms. So, um, so what do prostaglandins or eicosanoids, what are they capable of doing? They can lower or raise the blood pressure. They can stimulate contraction and relaxation, especially when it comes to pregnancy and the uterus. So we look at also it's responsible for pain or inflammation and pain. And you say you stub your finger accidentally pounding a hammer because you're just tired and you missed a nail and hit your thumb. And so now you introduce pain, and this arachidonic acid can be signaled to be turned into a prostaglandin. For example, it could be PGF2, which is there's other PGFs, prostaglandins 1, etc. There's many of these. And you see the 5-membered ring is made here, and the molecule is changed a little bit. You lose some degrees of saturation, but it's sort of now you have a signaling molecule, and it can introduce the sensation of pain, fever, and signal for inflammation. And inflammation is a whole process of where many uh, cells arrive at the spot of where there is danger because signals have been sent out to the body to cause the immune system and the repair system of our body to react, and we get inflammation. And we have NSAIDs, which are non-steroid anti-inflammatory drugs such as aspirin, which can block the production of prostaglandins. Although they're not steroids themselves, they can have an effect on this prostaglandins steroid-like molecule. I shouldn't say steroid. It's not like cholesterol, and it's not exactly like a long-chain fatty acid, is it? It's turned into this ring with a couple of very long chains coming off this 5-membered ring. It has hydroxylations here. You don't see that here, right? How did hydroxyls magically get onto this arachidonic acid? How did these double bonds get moved around? How did a hydroxyl get here? All from the use of an enzyme. All this work done to make arachidonic acid into PGF2 came from enzymes. And once that's done, you then get to feel the wonderful sensation of pain, fever, and inflammation, which is signaling things about your environment, by the way. So arachidonic acid can make many of these prostaglandins, and you can have PGF2 that we just looked at, PGF1, and PGE1. And this can be the arachidonic acid as a prostaglandin in different tissue. Different tissue has different variants of the prostaglandins. So NSAID, like we looked at aspirin, it can also be naproxen, which is in Aleve and naproxen, and ketoprofen, Actitron, and nabulitone, which can be Relafin. So there's many of these NSAID blockers. So omega-6 acids, this is where the naming goes a different route. The naming of where the, remember how I told you the first, if you count from the carboxylic acid, often the first unsaturated point will be at carbon 9. Not always, because you see in arachidonic acid, that's not the case. It's 1, 2, 3, 4, 5, where the 5 is 6, 7, 8, 9, and in 9, so that's not a surprise. But we often name the fatty acid from the end of the chain, from the very simple part of the molecule, and we count from there 1, 2, 3, 4, 5, 6. So omega-6 fatty acids have the first double bond introduced 6 carbons in from the end of the chain. And our arachidonic acid, the same thing, 1, 2, 3, 4, 5, 6. So these both linoleic acid and arachidonic acid could also be classified as omega-6 fatty acids because their first double bond or point of unsaturation comes at carbon 6 from the end of the chain. And we're doing, for the first time, we're not counting from the front or the most oxidized part of the chain, right? Remember, we did that for sugars and fatty acids and everything up to now. So there's other ways to name these things. These are omega-6, but we do have omega-3s as well. Um, so unsaturated fats in vegetable oils and fish are often recognized as more beneficial to our health than the saturated fatty acids because they can harden easier, they can stick together easier, and they can slow down things in the bloodstream. Whereas things with unsaturation can make things work very fluid in the bloodstream and not clog up the system. Not that saturated fats are always going to be your undoing, but too many of them, who knows, right? It depends on many factors. Now, vegetables contain omega-6 acids, which is what we see with linoleic acid here, and arachidonic acid, which is in meats. So it's not just vegetables, but so example of omega-6, we see that right in front of us. Both of these are omega-6. We'll see some omega-3s in a second here. Now, fish have high levels of omega-3 acids, and you can imagine what that means. That means if you count from the end of the carbon, you go to the 1, 2, and 3 carbon, you start to get a double bond. You get a point of saturation even earlier than you do with the omega-6, right? So they're in fish, and cold water fish often have lots of omega-3 fatty acids. Um, And here we go. Just some examples of omega-3s. Linolenic acid, 1, 2, 3. EPA, eicosapentaenoic acid, 1, 2, 3. Omega-3. Docosahexaenoic acid, DHA, 1, 2, 3. All of them have the 3 as the start of their point of unsaturation. And this one has 3 unsaturation bonds. This one has 1, 2, 3, 4, 5 degrees of unsaturation. This one has 1, 2, 3, 4, 5, 6 degrees of unsaturation. And guess what? The name here, hexa, refers to the 6 double bonds of unsaturation. And here, pentanoic, the 5 double bonds, is part of the name. So I'm not going to get deep into naming these because even I don't know all the names for all these fatty acids, and the rules try to stick to some semblance of order. But more important is that we know that these are omega-3 fatty acids, and the first point of saturation starts at the end. And notice they have different lengths in their carbon. This one's 18, this one's 22 carbons, this one is, or excuse me, this is 18 carbons, this is 20 carbons, this is 22 carbons. So when they talk about atherosclerosis and heart disease, the cholesterol, the four-membered ring can help, unfortunately, form plaques that adhere to the walls of the blood vessels. Blood vessels themselves are kind of non-polar, and cholesterol is non-polar. And so if things get clogged up, this can become unfortunate. What happens is the blood pressure rises as the blood vessels become blocked, and they get smaller and smaller because of these plaques forming. And there's a possibility of blood clots and clotting of vessels and causing a heart attack. And many people are hoping that it gets to the point where we don't really have to always operate on people, that we can do this through some drug or some process that can open these blood vessels up. So, but if you're a heart surgeon, hey, you got to do what you got to do with the technology you have. So omega-3 fatty acids can lower the tendency of blood platelets to stick together. That's another part of blood clots. It takes cholesterol and adherence to the cell walls and blood platelets and all sorts of bad stuff happening for a heart attack. So omega-3 fatty acids can help lower that possibility. So are these saturated, monounsaturated, or polyunsaturated? So let's look at this. Linolenic acid, palmitoleic acid, and stearic acid. So uh, again, polyunsaturated for linolenic acid. Look up the structure if you're unsure. It has multiple double bonds. Palmitoleic acid only has one double bond in it, and in stearic acid has no double bond. So it's a saturated, um, uh, and it's of course going to be not as fluid because it has no double bonds in it. And that is the end. You guys have an awesome day. This has been GOBC Chem 114. I'll see you soon.